Hello, hello, hello. I hope you're doing well. Today we are going to start Module E2 on Taylor's series. Essentially, we are entering and exploring a new world where polynomials have infinitely many terms, and we're going to try to see what does that mean for us in the context of approximating functions. But before we dive in, I do want to take a step back and look at some really important revisions from the previous video. So right now I am on our Quarkus course page, and I'm just going to highlight, here's the Module E1 stuff. The first important handout is right here. It's titled E2 Important Details for Slide 10. I'm just going to jump in there and show you what's relevant. Okay, so for this video, there were actually 2 rounds of corrections. So if you were a keener and you watched this video within the first 2 days of it being posted, I encourage you to go back and just make sure that you actually have the most updated revision, because I actually corrected and then had to correct my correction. So please do go back and make sure that you have the most updated handout if you downloaded anything, because this is really important stuff, and here I actually give a much more thorough and rigorous explanation than what was in the video. For the next revision, it's here. This is the next handout. It was for the cheesecake exercise, so I'm going to go right in there and show you what was important for that one. All right, so here is the document. I already have it scrolled to the area that I want it to be. This is where I actually looked at the kth derivative at 1 and actually broke it up into kind of a piecewise type of function, because our anchor actually doesn't fit the pattern. And that's something that you might see from time to time. And so I just showed you this form with the hope that it would be helpful in kind of breaking things down and seeing why, in this particular case, I didn't end up with a lower limit of 0 on my sigma. The other detail is just at the end. I initially had the wrong upper limits here on the sigma, so that those have been revised. And also just an important detail that for the final solution I ended up rounding up, but I give you the specific reason why. So we shouldn't just be randomly rounding up or down. We should be thinking about what the question is asking for when we make those decisions. All right, for today's agenda, we are going to start first with a PCE check-in and a couple of definitions. From there, we're going to move on to making sure that we understand what it means for convergence or divergence of a series. And then we're going to talk about some celebrity Maclaurin series. Remember that Maclaurin just highlights that the center is 0. From there, we're going to move on to the estimation theorem for alternating series, which gives us an alternative to Taylor's theorem, which was last video. And then finally, we have some play. So we're going to get into a couple of exercises just to make sure that we understand how to apply all the goodness that we've learned. All right, for our check-in today, it centers around vocabulary. So basically, I want you to just match the guys 1 through 4 with the A through E, and there might be more than one of these that connects to the 1 through 4. So let's take a moment to pause and reflect, and we'll be back in just a moment to discuss the results. Okay, let's discuss. So the first one asks about Taylor's series. So hopefully you were able to identify that B goes with this guy. The second one is a series, and in your PCEs it talked about how a series is a sum consisting of infinitely many terms, and then of course Taylor series is a particular kind of series, and so we can go with both B and D here. For this guy, it's asking about what it means for a series to converge. This was also in your PCEs, and so the idea is that we have convergence if we take the limit of what we call the nth partial sum, and that it exists and is finite. So here we've got A. And then finally, divergent, we look, and I mean, really, it's the only things that are left. But here, we've got C, which is the limit of n approaches infinity. So if that limit is infinite, then we have that it diverges. And if the limit does not exist, we have divergence as well. On this slide, I just give you the formal definitions for Taylor series and convergent or divergent series. So what we just pretty much did some matching for, but kind of more formally stated. And so the only thing that I think I really want to highlight for you here is this lovely symbol here, right? And so I remember what we talked about in terms of this idea of letting our number of derivatives continue to be able to take derivatives without end, right? We have derivatives of all orders here such that we can build a series, or in this case a polynomial with infinitely many terms, and use that to approximate our functions. This slide is trying to get you acquainted with the idea of convergence or divergence and when do those things occur. And so here I want you to just take a moment. I've given you a sum. This is a series. There are infinitely many terms here. And I just want us to ask the question, is it possible to arrive at a finite sum given that S consists of infinitely many terms? So I'm going to give you a moment to pause and reflect, maybe even play a little bit. And we're going to come back and talk about this. Okay, I hope you're ready. So the answer to this question is yes, it absolutely is possible. And we're going to be exploring that a lot more today. To really kind of highlight this, I think what I want to do is ask you, this sum here, is it familiar in any way? Does it look like a number maybe that you know of, that you've seen before? And I want you to think back to your base 10 number system. Remember, we have behind the decimal point, we have a tenths place, then a hundredths place, then a thousandths place, right? These powers of 10 are giving us our place values in a decimal number. So what this guy really is, this is really just a 0.9 repeating. And so that's a really interesting moment, because what I also want to ask you is, this guy, if it has a repeating decimal expansion, then that means that it's a rational number by definition. And that means that there exists some a and b that are integers where b is non-zero, such that 0.9 repeating is equal to a over b. Does anyone know, can you think about what would that number, that rational number be, a way to represent this guy as a fraction? You know, in fact, this is probably one of the first numbers you ever learned in your life. Probably the one that has come up the most often. Let's explore a little bit how we can unpack what this guy actually equals. So what I'm going to do is I'm going to say, you know what, let's let x equal to a 0.9 repeating. But notice that it doesn't matter where I put the bar, I can put it at the second one. You'll see why I'm doing that in a second. So then if I multiply by 10, then the decimal point just shifts over one place and I get a 9.9 repeating. And so what am I going to do with that? I'm going to subtract these guys, and I'm going to have a 10x minus an x. This guy was 9.9 repeating. This guy was a 0.9 repeating. And if I do this subtraction, I get that the repeating part disappears. I'm left with a 9 over here, and on this side I'm left with a 9x. And so lo and behold, what do we have here? We have a 9x equal to 9, dividing both sides by 9. We get that x is just a little old 1. And so here what we have done is we have represented the number 1 as a sum of infinitely many terms. We've seen that it actually is just equal to 0.9 repeating. And so this is a really cool result, really powerful one, I think, to highlight how interesting the math can get when we are talking about summing infinitely many terms. So in this slide, we're just going to build over top what we did in the previous one. The previous one we did purely algebraically. Here I'm going to try to get us to think about things geometrically. And so what I've done is we're also going to try to represent the number 1. Here we've got a interval of length 1, and all I'm going to do is start thinking about how I can show you visually what these guys represent as it pertains to lengths, right? So our 1/2 is here. We cut the whole segment in half, and then from there we can now cut this guy in half, which means we're looking at a quarter, right? Which is 1 over 2 squared, right? If we keep dividing by 2. And then I take what remains and I can also cut that in half. That's going to be a quarter divided by half, which is going to be 1 over 8. And then I can take that remaining eighth and I can also cut it in half. That would be here. That's going to be a 1 over 16. And the real numbers are what we call dense. And so that means that theoretically speaking, I can continue to slice this guy in half and then come over here and slice that guy in half and then come over there and slice. And I can slice no matter how thin those intervals become because of the denseness of the real line. And so we absolutely can continue to build and have a sum that has infinitely many terms, but such that the combination of all of those values sum to a finite length in the interval. Next, we're going to go to GeoGebra just so that we can see what's happening in a two-dimensional space. So here's the GeoGebra page. This is a square of area 1, finite area. And what we're going to do is we're going to do a similar kind of slicing up. And we're going to see if we can actually represent that sum, that infinite sum, using this. Right? And so we continue. You can see the sum starts to look closer and closer to 1, right? And then, of course, you know, it gets so small that we can't really continue in a way that we can see. But hopefully you get the gist, you get the idea of what's happening here. So in this slide, we are going to try to connect our previous results to a very popular and important series. And so let's first go back to Module E1 Part 1. I'm just reminding you of our work with f of x equal to 1 over 1 minus x. We had actually found its Taylor polynomial and a general derivative. And the first question just says, do the derivatives of all orders exist at x equal to 0? Hopefully it's clear that that is a yes. Notice that no matter what, we can always plug in the x. We'll never have a 0 in the denominator. And so for every k, this is going to be a defined expression. And so that means we absolutely can build our Taylor series. And so remember, all that means is that we're going to take the nth partial sum and we're going to let n go to infinity. And so our series, it has a very popular, well-known name. It is the geometric series. And this guy simply looks like sigma k equal 0 to infinity now. And now it's going to be an x to the k. And that just looks like a 1 plus an x squared, x cubed, and so on. Just a few important details. I'm not going to write them here. I've actually got some pre-written stuff over here. I just want us to make a few observations. Here are some values of x that we can plug in. We've actually already seen this before, right? If we plug in x equal to 1 over 10, what does that mean for the series? What does it mean for the function, right? When we plug in 1 over 1 minus x, plugging in 1 over 10. And a nice question to ask is whether or not these guys are going to produce the same output. Does the series, which is a sum of infinitely many terms, always necessarily produce the same as whatever the function will? So I'm just going to reveal to you my work here, where I just kind of opened up some parentheses, expanded, and then I landed an expression that we had actually seen before, right? And I landed a 10. Here, very basic work with fractions. Canceling, landing a 10, and it turns out that I ended up with doing the same thing, getting the same kind of result, right? Remember, we had seen this already. That should be a 1 up there. But we had already saw this geometrically, and we saw this algebraically, that these guys equal 1, and so we end up adding, and we absolutely end up with the same result here. And so it leads to some really interesting questions of whether or not this will always happen. Will the series always yield the same value as the function? And so let's see that in the next slide. So in this slide, I have some reflective questions that build over top some of the things that we saw previously. And I hate to rain on anyone's parade, but you know, the reality is that what I gave you was really nice, ideal circumstances, and that we absolutely will not be seeing convergence generally for all x real. I also want you to think back to the graph of the 1 over 1 minus x when we were playing around with GeoGebra, right? We did not see that we got a progressively better approximation once we passed a certain point of x values. But I also want you to look at this question here, and maybe, for example, for this guy, look at, what is f at 3, right? And what is this guy? This guy looks like a 1 plus a 3 plus a 3 squared, right? And ask yourself, should they be the same? Why or why not? And we'll pick it up in the bonus video where we talk about why convergence only happens for absolute value of x less than 1. So on this slide, we address the very important question of when does a function equal its Taylor series? And so to do that, I introduce a definition and a theorem. The first one is a definition. It gives you what we call the radius of convergence. And basically, geometrically, all it's saying is how far can we go? What is the distance that we can go either to the right or to the left of A such that our series converges? And so in this course, we don't care about the endpoints. We're not going to look at where we actually land at the ends. We just want to know that all values inside of this radius are values at which the series will converge. And so if r is finite, right, then it's just the distance. If it converges everywhere, we say r is equal to infinity. But remember, infinity is not a number. It just means that we get convergence over the entire real line. And if it only converges at the center, then we have that r equals 0. For the theorem, it says that we suppose that the function f has all derivatives of all orders, such that we contain the center. And then how do we get equality? Well, we absolutely positively have to have that the remainder term goes to 0 within whatever radius we are interested in. And so if the remainder term goes to 0, then we know that we actually can land equality between the function and its series within that radius. On this slide, we try to take a look at whether or not we can make any generalizations. So it says if a Taylor series converges within some radius r, then it equals its function for all x within that radius. So I want you to take a moment to pause and play or reflect, and I'll see you back in just a moment. All right, so let's talk about it. So hopefully by now you're getting like a bit of a red flag every time I start talking about generalizations that we should be very careful. This one is false. And let's talk about why. When we go back to that definition about radius of convergence, it says nothing about the actual function. It only talks about the series. And so to converge does not mean to converge to the function. And that's not a guarantee. Even if it does converge, it might converge to something else. And so it's really important that we don't, again, make gross generalizations outside of what the statements are actually saying. I'm going to give you a quick little example just so that you could see that this is a poster child example of a series that converges but doesn't converge to the function. And I just want you to watch the remainder. Remember that in order for them to actually be equal, the remainder has to go to 0. And I want you to see what happens with this remainder. All right, so this is our guy. It's a piecewise function. It's continuous. What we've done is we've put in the point 0, which is what the limit is of the function. And so we do have a continuous function. You can actually calculate the derivatives using the limit definition. And so everything is good. But as I increase my n, notice that the polynomial stays 0. And in fact, it will be 0 all the way through, and the remainder doesn't change as a consequence, right? So the remainder doesn't go to 0. The polynomial totally converges to the line y equals 0, but that is absolutely not what this function is. All right, it's time to play. So this exercise wants us to look at cosine's Maclaurin series and also for us to show equality. And so we get to use the goodies of that amazing theorem that we saw recently. And also for part B, your PCEs took care of this for e to the x. And so I'm about to take care of it for cosine of x, and it's identical, like the process is the same for sine. So we're pretty much good there. I'm going to ask you to pause here and play. Try to see if you can move through parts A and B. And when we come back, we're going to unpack both of them together. I'll see you in a bit. Okay, so we're back. I'm going to just fast forward through some of these calculations just because it's more procedural. And then once we get to looking at patterns and things like that, I'm going to slow it down again. All right, folks, so just a quick step in. What I noticed here is that we started with cos, and now we're back at cos again. And so basically what we have here is what we could call a 4 cycle, right, up until where we repeat. And so we know exactly what the pattern is going to look like moving forward. All right, so here I just highlight that we notice that for all odd values of k, right, we've got that the derivative disappears, right? This was k equal 1, this is k equal 3, and this is, right, so k equal 2 is here, is my even stuff, right? And so why is that relevant? Well, we want to try to build our pattern, and it's kind of helpful for us to pin down what's happening with even and odd stuff. So let's see if we can do that work with getting the pattern down. So our p of x, our series, is going to look like, we're going to have our anchor, so it's going to be a 1 over 0 factorial times x to the 0. And then if you want to write it all out, that's totally fine. That's a great way to make sure you don't lose anything. And then from there we have this guy disappears, the odd guy disappears, and we jump right to the even guy. And so we end up with a minus 1 now even 2 factorial x squared. Odd guy again disappears, even guy plus now 1 4 factorial x to the 4th, right? And so we can see, and now we're about to repeat the pattern, right? The 4 cycle is going to come back again, and so we're just going to keep seeing the even stuff happen. So it's going to be a 1, example, 6 factorial x to the 6, and so on. And so writing it as a sum, we can see the pattern pretty nicely. We got k equals 0 to infinity. And now we know we need alternating signs, so we're going to go -1. Starting at 0, we're positive, and so we can just start at k and let it alternate from there. The powers are even, and so how do we represent even numbers? 2 times some integer k, and the denominator is just the 2k all to the factorial. All right, for part B, we're asked to show that we get equality between cosine and its Taylor series that we just found in part A. So by theorem, we know that we have to show that the limit of the remainder term goes to 0 for all real numbers x. And so how do we do that? Well, by Taylor's theorem, because we need that. What do we know? We know that the absolute value, the absolute error or remainder is less than this. Absolute value of x to the n plus 1. And just remembering where everything is, we know that the n plus first derivative at some c is what has to be less than or equal to m. In this case, c is in the interval from c is between 0 and x, right? We don't really know what's going to be bigger than what because we're checking for all reals. So now what we do is we note that for f of x equal to cosine of x, we've got that the n plus first derivative, hopefully this makes sense, it's either going to be plus or minus sine of x, or it's going to be plus or minus cos. Right, they alternate. And so that means that if we take the absolute value, and let's go ahead and put that c in there. If you take the absolute value, it's going to be equal to either plus or minus sine of c, or absolute value of plus or minus cos, which is just, again, going to end up being plus or minus sine or plus or minus cos. And so that means that this guy has to be less than or equal to 1, and that's because we know that, you know, absolute value of sine is less than or equal to 1, and same for cos, no matter what c is. Right, because that's the range of these guys for all c real. So thus, we just take m equal to 1. And so what does that tell us? Well, it tells us that our remainder less than or equal to 1 over, this is me just substituting in the 1 in place of the m, right? This is from Taylor's theorem. And folks, properties of absolute value inequalities say that I can open this up, and it's going to be in between this guy and it's negative. All right, and so from there, what we're going to do is we're just going to take a limit. So here what I have written is that we've got the limits in there. Recall now we've got this squeezing happening. Recall that the n plus 1 factorials will grow faster than the absolute value of the x to the n plus 1 as n grows larger, right? Arbitrarily large. Factorial is the faster growing guy. And so what it's going to do is it's going to send those limits, and I missed it here, to 0. And then squeeze theorem gives that the limit as n approaches infinity of our lovely remainder guy has to equal 0 for all x real. In other words, our radius of convergence is infinity. On this slide, I just have some really popular celebrity Maclaurin series that get VIP status. Of course, these guys are going to get it. You know, their radii of convergence are infinite. They have the whole real line about which we have equality, which is amazing. This guy, even though the radius of convergence isn't great, it is going to help us so much when you get to the work with Professor Sinclair. There are so many other functions that we can get as a consequence of this guy. A couple of them are y is equal to ln of 1 plus or minus x. Another one is y equal to arctan. And so just make sure that, you know, once you get to this portion with Professor Sinclair, that you know how to manipulate this guy to get there, but also that you know how to arrive at all of these lovely guys, which we did the work. So hopefully you internalize that. On this slide, I'm introducing to you another theorem that helps us with bounding, errors, estimations, particularly for alternating series. And so, not sure if you noticed, but sine and cosine are alternating series. And so this will come in handy provided that all of the hypotheses of the theorem hold. And so here it tells us that the terms, you know, once we remove the plus or minus, should be greater than or equal to 0, and also that we require that the terms are decreasing. And so we just need to make sure we're checking the hypotheses before we use the theorem. But aside from that, once we have the hypotheses, folks, look at this. The error bound would just be the next term that we remove, which is so straightforward and amazing. So we're going to do an exercise in just a minute to see what that looks like in real time. So we're down to our final exercise of the day. It's called Hamster's Wonderland. I don't know how many of you got that in terms of Canada, but we'll see. So you're building a Ferris wheel for your friend's hamster because you're an engineering student and sources of entertainment are rather limited these days. So the Ferris wheel has a radius of 1 meter and moves counterclockwise to complete one revolution every 6 pi seconds. That's almost 19 seconds. The Ferris wheel is also positioned on a table such that the lowest point of the wheel is 10 centimeters above the table surface. Suppose that you place a hamster in the bucket seat at the highest point of the Ferris wheel at time t equals 0. We want to determine the minimal number of derivatives required to build the appropriate Maclaurin series that approximates the hamster's height above the table after 3 seconds, such that the error is less than this number. Okay, so I'm going to give you all a moment to pause and play, and then when we come back, I'll show you what I got. All right, so just an FYI, I'm going to post the link to that video that you saw in the corner on the slides, so you'll be able to access it that way. Let's go ahead and dive into the exercise. So what I have for you here is for my sample solution. I'll post the full solution. I'm not going to build the model here because that's your grade school stuff and I don't want us to lose precious time. Let's see if we can implement the calculus stuff that we learned during today's lesson. So if this is my model, let's hope I did it right. If this is the correct model, and there are many options, but this is the one I chose, then we must estimate cosine at 1. This is since h at 3 is equal to cosine 3 over 3 plus a 1.1, right? And so the cosine at 1 is the guy that's the troublemaker that we need to then do some work on. Using the estimation theorem for cosine's Maclaurin series, this is what we have. For x equal to 1, we know sigma goes from k equals 0 to infinity. We've got a negative 1 to the k, and now it's a 1 to the 2k all over a 2k factorial. Let's verify our hypotheses. Hopefully you can remember what they were. The first one was that our a sub k should be greater than or equal to 0, and in this case it absolutely is. Second condition was that the terms are decreasing, and that is also true. So then this is what we've got. It's going to be the first deleted term or removed term, which we have an expression for now. And we want this to be less than this value. So then from here, we test values of k to determine the minimal value that satisfies the inequality. Okay, so plugging into the calculator, we finally land the guy that we need. And so for k equal 4, this is what we have. Be careful not to say that k equal to 4 is the degree, yeah? Because remember that our guy was throwing out certain derivatives, right? It's really going to be the 8th power, right? That we are landing here. So minus. Okay, and so the minimal number of derivatives that we'll need here is 8. All right, so that pretty much wraps us up for today. Just a couple things. One, I will be posting that full solution, so do please look at it so that you can see what the full formal write-up is. I didn't actually write down the conclusion. You should write down the conclusion. I said it and didn't write it. The other thing is we used the estimation theorem for alternating series. We could have also used Taylor's theorem. And so just remembering that you've got multiple tools in your toolbox, but I mean, if you have an alternating series, this theorem is so much easier than Taylor's, I think. So just add another good tool to your toolbox. And aside from that, I hope you enjoyed the video. I hope you learned something today. And just remember that even though this is my last video, it's been such a pleasure making the videos for you all. You can always still find me for support, for drop-in, or anything. You can shoot me an email. We're all here to help. So just let us know what you need, and we'll do our best to make things better. Okay, so I'll see you around. Take good care. Bye.